Okay, hi everyone. Welcome to the exercise class. So let us slowly start. So today we'll cover 3 topics. So first we'll talk a bit about physical measurements. You already had them in the lecture and I also already mentioned them somewhat in the previous exercise class, but we'll go through it anyway. Then we'll go through FR thought experiment, which you already had in a lecture too, but it never hurts to go through it again. And finally, I'll briefly mention the weak measurements in Hardy's setting. And so all these 3 topics correspond to the 3 exercises that you have in the exercise sheet. So first, let us talk about the physical measurements. So as in previous exercise class and also in the lecture, we look at the examples of the measurement process where the system acting as a measurement device or a memory storage is modeled explicitly as an additional physical system. And it's good to remember that our main motivation to do so is because as quantum information scientists, we think that we're convinced that information is physical, and hence whenever we acquire certain information, we have to store it in a particular physical system. Okay, and so let us look at different cases, and remember that the scheme that we're considering is called the von Neumann scheme, where we look at the system plus measurement device. And first, let us consider the discrete case. How can we model a physical measurement in a discrete case when we're, for example, are measuring a qubit? So suppose that we have a qubit S. Then if we measure a qubit in its computational basis or Z basis, then we get either the outcome 0 or the outcome 1, which means that we can actually use another qubit, another 2-level system to store this result, which we'll call system M. Then, for example, for the active measurement in the Z basis, kind of the measurement or the memory update, as we can also call it, can be just described by a C-node gate. And the C-node gate, just to remind you, is basically a controlled X gate. So it flips the state of the, sorry, it seems that you cannot see what I'm writing. Let me reload the sharing. Okay, now it should be good. So the C-node gate is basically a controlled X gate. So if the state of the control qubit is 0, nothing happens to the controlled qubit M. If the state of the qubit S is 1, then the state of the qubit M is flipped. So basically, the C-node gate can be written as if the system S is in a state 0, nothing happens on system M. And if the system S is in a state 1, then we apply the X operation on the system. So as I said, this can be seen as measuring S in Z basis and writing down the result to M. Why? So for example, let us consider that the state of the system S is alpha 0 plus beta 1. And let us also assume that the system M is initialized in the state 0. Then the C-node operation basically maps the state to the following state. So The first part, because the system S is in the state 0, nothing happens on the memory. So we just get alpha 0, 0 SM plus beta, because here the state of the control qubit S is 1, the state of the system M is flipped. So we get beta 1, 1. And we see here that this is exactly the coherent copy operation that we will be looking for, that we measure the system S and 0, 1 basis, write down the result to the memory M. And indeed, these two systems are correlated in this particular way. So in the exercise sheet, you're going to look at the physical implementation of this, namely a particular Hamiltonian that can implement this unitary gate, but then you'll need to calculate what is the time that we need to turn on this interaction Hamiltonian. Okay, so this was a very simple example of kind of this measurement scheme for the discrete case. And now let us go to the continuous case that we also already had previously, or like briefly talked about previously. So a good example of kind of this measurement procedure in a continuous case is the Stern-Gerlach setup. So Stern-Gerlach setup, as you might remember from some physics course, is a setup which allows us to measure the spin of the particle. So basically, we have here a particle. Suppose an electron which has a spin, spin modulus 1/2. Then we put it in the we put it such that it passes through the magnet, which is kind of this interaction zone. And then since the spin interacts with the magnetic field created by the magnet, we would have two patterns on the screen, two distinct patterns on the screen far away from the interaction zone. Each one of them corresponding to either spin 1/2 or spin minus 1/2. And the intensity of these peaks would correspond to to the ratios of the spin half and minus 1/2 in the superposition here. But so just to formalize the situation, so we have an electron which is moving in this plane, and this electron has 3 degrees of freedom. So the degrees of freedom are, so first is the spin degree of freedom, and the second degree of freedom is the orbital degree of freedom in the x direction, and then the orbital degree of freedom in the y direction. So let's say that this is x. Let me get the other way around. So this is y, and this is x. And each degree of freedom corresponds to a particular Hilbert space in the decomposition of the total Hilbert space, which describes this electron. And the first spin degree of freedom is essentially just a two degree of freedom system. So we are not really interested how the electron was moving before the interaction zone. We are interested what happens in the interaction zone when the spin gets coupled to the movement of the electron in a particular direction. And this can be described by interaction Hamiltonian, which couples these two degrees of freedom. So it couples, in our case, degrees of freedom corresponding to spin and to the movement, to the position in the y direction. Yeah, sorry, something happening today with my screen sharing. Yeah, that was good. So yeah, and then we can write this interaction Hamiltonian as just coupling of the Z operator in the spin degree of freedom, then nothing on X, and Y, the position operator in the Y direction. And then the idea is that since we kind of intuitively already know, or experimentally, we also know that the indeed on the screen we see these two distinct peaks corresponding to two different spin projections. So we'll just start with a particular initial state of this electron, and then just convince ourselves that indeed these two, like this interaction Hamiltonian, couples the degree of freedom of the spin and its coordinates in a y direction. So the initial state of the electron, we're going to take psi 0 tilde, which is the initial state of the spin degree of freedom, which is a qubit, so we can write it out just as this qubit state in the 0, 1 basis, which is the Z basis. And then the wave function in the XY, in the for the XY orbital degrees of freedom. And the wave function for the orbital degrees of freedom, we're going to choose it as a Gaussian wave function. So this will be a Gaussian. This will also be a Gaussian. I will not go into the details of like how you write out the Gaussian. It's just that the psi of x would be something like e to the power minus x0 squared over 2 sigma squared and so on. Or like maybe it's 4. I don't remember exactly, but I'm not gonna do the whole derivation here. I'm just gonna like give the idea of what you're gonna get in the as a result of this derivation. So if we take the initial state of the electron as such, then after passing through the interaction zone, yeah, let's say for the time tau or so, because in the interaction zone we couple like the y degree of freedom and the spin degree of freedom, then the state that we get will look as follows. So it will have like two components. So the x component will of course stay the same as before because we apply identity on that component. But the spin and also the wave function in y direction are gonna get entangled. So here the term that you'll have here will also be a Gaussian, but it will also depend on M, which here corresponds to the spin projection. And basically, because of this, if you then consider that after going out of the interaction zone, the electron moves for some time until it reaches the screen. We can model it as just moving under the free Hamiltonian, which is just the usual p squared over 2m. Sorry, mu, since m we're already using m for the spin projection. And then if you if you evolve this state up to the interaction zone using this free Hamiltonian, then essentially what you would get are these two distinct peaks on the screen. So this is the screen. So I would recommend to explicitly do the calculation to obtain the state phi of tau after the interaction zone to convince yourselves that indeed this coupling happens. And then you can either estimate or just by how the state looks like and what you know about how the Gaussian wave functions evolve, you can already kind of predict what would be the shape of these two patterns on the screen and their intensity. So kind of for the free evolution part, you don't need to do the whole calculation explicitly. Just kind of estimate what's going to happen and give like this a qualitative answer. Okay, so this was about the physical measurements, which are basically, again, coupling two systems or 2 degrees of freedom, and then storing the measurement result in the 2nd degree of freedom. Because, I mean, in Stern-Gerlach experiment, this is exactly what happens, right? Because we want to measure the spin, but we measure the spin indirectly by measuring the degree of freedom it's coupled to, which is the position, the y position on the screen. Okay, so now let us go to the second topic that we wanted to talk about, which is the FR thought experiment. Okay, so what is exactly the setting of this thought experiment? So we have, in this thought experiment, we have 4 agents: Alice, Bob, Orzo, and Wigner, and we start with Alice and Bob sharing a state of the systems R and S that they have access to, which is psi 0 RS 1 over square root of 3 0 0 RS plus 0 1 RS plus 1 0 RS. Just a small comment. So this thought experiment is based on the work done by Daniele Frauchige and Renate Renner. And there is a paper which is also referenced in the exercise sheet, and I'm sure Lydia also mentioned it. So if you look at the paper, the state that kind of Alice and Bob have, like after their machinations, is a bit different. So it looks a bit different, but it's the same as the state that we're considering here up to the permutations like up to switching the labeling of 0 to 1 and 1 to 0 in a first and a second system. So they're basically the same. Okay, and so let me maybe draw also the setting. So we have Alice in her lab with the system R. And Bob in his lab with the system S. And then we have two observers on the outside, Ursula and Wigner. Yeah, so the funny fact is that I've drawn this experiment so many times that on my website I even have a dedicated section of my art, which is just about different pictures of this setting. But in any case, so the crucial point of this experiment is that Alice and Bob, which measure the systems R and S, are also modeled as physical systems. And coming from just the consideration of our physical measurement that we were just having earlier today, this makes perfect sense because after the measurement of system R, we need to store the outcome that we have obtained somewhere. So it makes sense to model the memory which stores this outcome explicitly as well. And then the following protocol happens in this procedure. So at time t equal 1, Alice measures R and writes down the results. At t equal 2, B measures S, writes down the result. At t equal 3, Ursula measures R and A jointly. So the whole lab here. In the basis, sorry, so I didn't mention here. So here A measures R in 0, 1 basis, and S, Bob measures S also in a 0, 1 basis, and Ursula measures R and A jointly in so-called OK fail basis. Where OK on RA is 0, 0, minus 1, 1. And fail is 0, 0, plus 1, 1. Then at time t equal 4, finally Wigner measures B and S jointly in the basis OK SB, fail SB. And OK and fail states that Wigner uses are essentially the same states that Ursula uses up to the subsystems that they're applying this measurement to. Okay, and as you've seen in the lecture, there is a particular inconsistency arising given that the agents are allowed to reason about each other's outcomes if this reasoning is done with certainty. And so here we will just go through the kind of this thought process again. So first, we kind of calculate the state just before Ursula starts to measure A's lab, so systems R and A jointly. And so this is just after B measures system S and writes down the result to his memory. So if we just again remind ourselves of what kind of this writing down to the memory means, this measurement means, for the discrete case, and this is a discrete case because systems R and S are qubits, and the memories A and B are also qubits, then basically each such writing into memory operation is just a CNOT gate, or like this coherent copy gate. So if we start with a state which is labeled up there as psi0 RS, I'll just rewrite it here. And also assume that our memories of A and B are, so this is at time t equals 0. Our memories are A and B are initialized in a state 0. Then what happens after this memory update for each of the systems A and B is that essentially the entry that we have in the for the systems R and S gets coherently copied to the systems A and B. So for example, here, if the system is in a state 0, then this stays in a state 0, and here the system R is in a state 1, so the state of the qubit A will be flipped, or the memory A will be flipped. So then at time, like after Alice at time 2.5, after Alice and Bob measure, we end up with the following state. So 0, 0, RA, 0, 0, SB, plus 0, 0, RA, 1, 1, SB, plus 1, 1, RA, 0, 0, SB. Okay, so this is the state before Orzo and Wigner start to measure, and this is the state on a base of which we're going to make our conclusions about this agent's predictions. But before we start making these conclusions, we add another aspect to this experiment. So we have Orzo and Wigner measuring in this okay-fail basis, right? So let us just post-select on a particular event of both of them getting the outcome okay. So we just run the experiment as long as, so we run the experiment until they both get the outcome okay. But one can say that maybe this is not true. So maybe they will never get outcome okay, but this can be easily shown by just calculating the probability of them both getting outcomes okay. So yeah, maybe here for convenience, I'll just drop the subscripts corresponding to the time of the measurement, or like on which step the measurement was made. But basically, what I want to say here is that we post select on the both getting outcomes okay. And the probability of this event can be just calculated as, so we need to project our state, which let me label this as psi R A S B. So we just need to project our state first into Ursula getting okay, and then Wigner getting okay. So we have okay, okay, on the systems SB, tensor product, okay, okay, on the systems RA, and this all calculated given the density matrix psi0, psi0 on all 4 systems. And we calculate the trace of this, and this gives us the probability of Ursula and Wigner both getting outcomes okay. I will not do this calculation here, but I'll just give you the final result, which I think is 1/12. But here you can just do it whatever by calculating this by matrices or just writing it out explicitly. Okay, so kind of our starting statement that's let us assume that both Ursula and Wigner get outcomes okay is justified because the probability of such event is non-zero, and we can just wait long enough until this round comes to be. Then to show the inconsistency arising, we just need to prove the following inferences which form a chain. So if Ursula gets outcome okay, then B gets outcome 1. So again, just to remind you of the state, sorry, not psi0, but the state that's the final state, psi RA SB, which is 1/3, 0, 0, RA 0, 0 SB plus 0, 0 RA 1, 1 SB plus 1, 1 RA 0, 0 SB. Okay, so let us see how we can prove this inference. So to prove this inference, we just need to calculate. So one of the way to prove this inference is just to calculate the conditional probability of B getting outcome 1, given that U got outcome okay. Which means that first we have to project the state into the state corresponding to Ursula's measurement okay, and then just calculate the probability of B getting outcome 1, which basically means that have 1, 1 on the system S, on system B, then this is the first projector. Then we have the projector of Ursula getting okay on the systems RA, and then we have our psi. And then we have to normalize it over our condition, so U getting outcome okay. So this is how we calculate the conditional probability, and one can show that this is equal 1, which means that indeed our inference is valid. Similarly, we can calculate the conditional probabilities for 2 other inferences and also find that we can make them with certainty. So the probability of these inferences is 1. So these inferences are from b equals 1, it follows a equals 0. So here the probability of a equals 0 given b equals 1 equals 1. So this is fairly straightforward to see, actually, because the only term in this state which corresponds to b getting outcome 1 is this middle term. So the first projection will essentially collapse our state into this term, and then we only have, and here we only have the term corresponding to a getting outcome 0. So this conclusion is fairly straightforward. And the final conclusion is that if A gets outcome 0, then Wigner gets outcome fail. So this basically corresponds to the conditional probability of Wigner getting outcome fail, given that A equals 0, which is 1. And then I recommend you going through these calculations yourself, because when you see this for the first time or the second time even, you always have a sneaking suspicion that there is something wrong with the calculation, but there is nothing wrong with calculation. But still, it's good to convince yourself that it's true. But taking this for inferences. Sorry, so we start with this post-selection, then we take the 3 inferences. So from u equals okay, it follows b equal 1. From b equal 1, it follows a equals 0. From a equals 0, it follows that b equals fail. And what we get is that from v equal okay, it follows that v equal fail, which basically gives us the inconsistency. Okay. So this was essentially calculation-free content of the exercise 2. And now let us switch gears to
Sorry, can you run over the assumptions that are made for this process?
yeah, sure.
I'm kind of lost.
Oh yes, so
and also like for this to be inconsistency, like some steps in the logical flow should happen, right? Like B should be 1, and then it's only inconsistency, or not?
Okay, so let me explain all of this. So this is a very good question. That's always a very good question to ask when you see some weird thing happening. You always ask, okay, what are the assumptions that you base this on? You base your conclusions on. So there are 4 assumptions which go into how we derive this inconsistency. So the first assumption, we can call it the assumption Q, or is usually called the assumption Q, which basically means that the agents are able to use Born's rule, or like actually only the Born's rule, which applies to the certainty, to the probability 1 events to make their inferences. So for example, this Q, let's just say like Born rule for probability 1. So they're basically able to calculate that this inferences hold true, which for example means that this conditional probability is 1. Then another assumption, which is the assumption U, which is sometimes taken under the umbrella of the assumption Q. It basically means that the agents to derive to model. Yeah, to model the evolution in other agents' lab, they assume that the evolution is unitary. So, and also while deriving the state, we assume that evolution is unitary. The next assumption is called the assumption C, which is the consistency assumption, which is, or not exactly, not exactly the consistency assumption, but it basically governs the rules of reasoning that agents can apply. So for example, it means that if agent A says that from A it follows B, and the agent B says that from B it follows C, then this rule allows us to say that agent A can say that from A it follows C. Because if we have these two, then if from A it follows B and from B it follows C, then logically from A it follows C. But here the assumption is also that A is able to use B's point of view to combine these two inferences into one inference. And basically, like, this assumption C is about that agents can reason from each other's points of view. And finally, there is an assumption S, which is the assumption, which is also called single world assumption. It basically says that if we conduct a measurement, then as an observer, we only get one outcome, which basically means that, oh, if I'm Alice and I'm doing a measurement of the system R, I can always, so for me, the result of measurement is either 0 or 1. Like, there is no third option. Yeah, funnily enough, some interpretations, for example, many words, like extreme versions of many words interpretation, kind of are against this assumption. So it's like, oh, I measure the system, but then I know that I'm still in a superposition, so blah, blah, blah. So in any case, these are 4 assumptions that go into the derivation of this inconsistency. So, and then one can also look at different interpretations of quantum theory, and then see in which interpretation of quantum theory which assumption goes wrong. Okay, what was the second question? I already forgot. Does this answer your question? Or
yeah. Well, I'm not sure if I'm correct, but for this to be inconsistency, don't you need that one of the premises in this, like, contradicting loop is true?
Oh yes, this is the one we start from. So we always start with this event on which we post-select, where both Urzo and Wigner get outcomes okay, and then we unroll this chain.
Okay, then I get it. Fine. And this paradox is like not resolved?
Oh no. I mean, the point is, again, like this, the aim of this paradox is to, one of the aims of this paradox is to make a kind of more experimental distinction between different interpretations of quantum theory. And one can draw a table where essentially different interpretations would check out, would say that, oh, this assumption is violated, or this assumption is violated, which kind of in principle says that if there is a way to implement this thought experiments in real life, then like actually experimentally, then we would be able to get rid of some interpretations. So we would be able to pinpoint which assumption goes wrong exactly. Yeah, I would in that sense, concerning these paradoxes in quantum theory, I would recommend you. I mean, okay, I don't know how it's good to recommend my own papers, but Renato and I wrote just published a paper in the beginning of this year, which is called Testing Quantum Theory with Thought Experiments. And it's basically, I guess, most modern review of like the paradoxes that led up to this, and also this paradox, and how interpretations fit in, and also what are the most common criticism concerning this paradox. So if you're interested, you can check it out. Yeah, we tried to write it in a kind of in a way such that even like undergraduate students would understand it. So yeah, I hope it should be more or less comprehensible. Okay, so time is up, but let me just quickly add something about the last exercise, which is about the weak measurements in Hardy setting. So the idea here is that one of the possible objections to Hardy's paradox is to appeal to the contrafactual reasoning used to get this contradiction and say that, oh, okay, you're making these contrafactual statements. So you allow yourself to make inferences which do not actually refer to the results of any actual experiments. And so then this contrafactual reasoning is like does not hold. Like, why would it hold if it doesn't really reflect the real outcome of the experiment? But one way to remedy this objection is to appeal to the weak measurements, where we couple the system to the measurement device, and this coupling is weak. So it does not really disturb, or it does not much disturb the state of the measured system, but we are able to read out the measure, so the device, and then infer the state of the system indirectly for the measurement device. And this inferred value is called a weak value. And one can apply this concept to the Hardy's thought experiment and also see that via weak values, we're able to reproduce Hardy's result. And I also believe that Lídia will talk about weak measurements at length today in the lecture, so I will not go into detail.